Hey, welcome back. In this video, we're going to discuss relations. Relations are something that we've seen before multiple times in this course. Back when we talked about functions, we saw an example of a relation, and we'll discuss that a little bit later in this video. We also saw examples of relations when we discussed graphs. And here I mean both directed graphs and undirected graphs. And in general, a relation is a special kind of set. Specifically, if we have two sets, x and y, a relation from x to y is a subset of the Cartesian product of x and y. We're going to look at some examples of relations that we've seen before. We're going to start with directed graphs. Recall that in a directed graph, the edges have direction. Here's an example of a small directed graph. Here I've drawn two edges. One edge goes from vertex 1 to vertex 2, and the other edge goes from vertex 2 to vertex 3. Another way of writing the same graph is as an ordered pair, where the first element of the ordered pair is our vertex set, 1, 2, 3, and the second element of the ordered pair is our edge set. And the edge set we can write as ordered pairs, where the first element of the ordered pair is the vertex where the edge starts at. For this edge right here, it starts at vertex 1, and it goes to vertex 2, which we write as the second element of the ordered pair. Similarly, the other edge right here goes from vertex 2 to vertex 3. So we write it as the ordered pair 2, 3. So when we write an ordered pair u, v, it's just representing a directed edge from the vertex u to the vertex v. For this relation, both of the sets x and y are the same. They're both equal to the vertex set v. And the relation here is just the edge set. E, the edge set, is a subset of the Cartesian product of the vertex set with itself, which we write as v squared. And v squared is equal to the set of ordered pairs x and y, which are both elements of v. We're going to look at some examples now of graphs, directed graphs specifically, and we will see what is their edge set to determine the relation associated with these directed graphs. The first directed graph that we will consider is a directed path of order 4. It has 4 vertices because it has order 4, and a directed path has the edges pointing in the same direction. We will call its vertices 1, 2, 3, and 4. Here, the relation is the edge set, and we can write it as this set of ordered pairs: 1, 2, 2, 3, and 3, 4. And that's the relation. Let's look at another example. Now we'll look at a directed cycle of order 4. We still have 4 vertices, but now we get an extra edge. Here, the edge set, our relation for this directed graph, is the following set of ordered pairs. We have 1, 2, 2, 3, 3, 4, and 4, 1. We'll look at one more example. A directed star of order 4. Let's look at this one. And we'll say the center is 1, and the others are 2, 3, and 4. Here, the relation, the edge set, can be written as so. So we just saw a few examples of relations, and each of these relations were just the edge sets of directed graphs. We can also view undirected graphs as relations. Recall that an undirected graph looks different. We can take those same vertices 1, 2, and 3, but now our edges have no direction, and we write them like that. We can think of the edges here that I drew as subsets 1, 2, and 2, 3. And each of these subsets, we can actually write them as 2 ordered pairs each. So we take a subset u, v, where u does not equal v, and remember that that subset is the same as the subset v, u. And this subset we view as the 2 ordered pairs u, v, and v, u, with parentheses instead of subset brackets. Now our relation is the edge set, but instead of written as a set of subsets, it's written as a set of ordered pairs. And again, the edge set here is going to be a subset of the Cartesian product of the vertex set with itself, because we're representing the edges as ordered pairs of vertices. So we'll look at some examples now of the edge set written as a relation for undirected graphs. Here's the first one we'll consider, K3. This is the triangle graph. It has 3 vertices and all possible edges. And again, we're talking about undirected graphs here. So no arrows here. And we'll call our vertices 1, 2, and 3 for this one. The relation associated with this graph, the edge set written as ordered pairs, we can write it as so. 1, 2, 2, 1. These two represent the edge 1, 2 as a subset. We also have 1, 3 and 3, 1. And finally, we have 2, 3 and 3, 2. So we have a total of 6 ordered pairs there. And that's the relation for the edge set of this graph. Let's look at another graph now, a path of order 4. Since it's undirected, remember that the edges have no arrows on them. And we'll label the vertices as 1, 2, 3, and 4. Here the relation associated with this undirected graph is the edge set written as a set of ordered pairs, and we can write them as so. 1, 2, 2, 1, 2, 3, 3, 2, and 3, 4, 4, 3. And that's the relation. We'll look at one more graph. Just kidding. So we're going to talk about a slightly more specific type of relation, and it's a relation on set. So before, when we talked about relations, we said a relation from set X to set Y. When we have a relation on a set, the sets X and Y are the same. So a relation on set X is just a relation from X to X. And the relations that we just saw were actually relations on sets. So the edge relation that we saw for directed graphs and undirected graphs, both of these were relations on sets. And the set in both cases was the vertex set V. Here's another relation on a set. We call this relation divides. So divides is just a name of this special subset. And the set we're considering here is the positive integers, which I write as Z plus. So divides this relation. It's a subset of the Cartesian product of the positive integers with itself. And we define divides as the following subset, which is the set of ordered pairs x comma y, for which both x and y are positive integers, and the most important part, x divides y. And that's our relation. And as you can see, it's a relation on a set because this is a relation from the positive integers to the positive integers. And we can see what kind of ordered pairs that we get in this relation. So for example, we get all of the ordered pairs of the form 1 comma n, where n is a positive integer. And that's because 1 divides n for any positive integer n. We also get all of the ordered pairs of the form 2 comma 2n for every positive integer n. And that's because 2 divides 2 times n for all positive integers n. Similarly, we get all the pairs of the form 3 comma 3n, and so on. We can also view, like I said earlier, functions as relations. And the specific relation that we'll see here is something that we saw earlier when we studied functions. And what's interesting is it has the same name as one of the other things that we saw earlier in this video, which we can view as a relation. And that name is graph. So if we have some function f is from the set x to the set y, the graph of f is the set of ordered pairs x comma y, for which x is an element of the domain and y is equal to f of x. And I claim that this graph is a relation from x to y. And that's because it's just a subset of ordered pairs of the Cartesian product of x with y. And that's because little x is an element of big X and little y is an element of big Y. And that's because f of x is an element of big Y, because y, big Y, is the codomain of f. And we'll look at an example here. So let's consider this function. We have f from the set 1, 2, 3 to the positive integers defined by f of x equals x squared. So we can write the graph of f as this subset. It will have 1 comma 1 squared, which is 1. It will have 2 comma 2 squared, because 2 squared is f of 2, and that's 2 comma 4. And finally, it will have 3 comma 3 squared, the same as 3 comma f of 3, and that's 3 comma 9. And that's the relation associated with this function. That's the graph of f. Here is another relation. We will start with the set x, which is just equal to 1, 2, 3, and 4. So x has cardinality 4 here. And our relation is going to be congruence mod 2. So we're going to obtain the following subset: the set of ordered pairs x comma y, for which both x and y are elements of the set big X, and x is congruent to y mod 2. And let's look at what set we obtain there. So first, we can see that for any element of the set big X right here, any element over here, each of them are congruent to themselves mod 2. So we get 1 comma 1, 2 comma 2, 3 comma 3, and 4 comma 4. These are all elements of this relation. We also get more though, so we can see that 1 and 3 are congruent mod 2. So we get 1 comma 3, and we get 3 comma 1. Similarly, 2 and 4 are congruent mod 2. So we get 2 comma 4, and we get 4 comma 2. And that should be everything. And we can see here that this is a relation on a set. Our set is just x, 1, 2, 3, 4. So now that we saw a bunch of examples of relations, we're going to look at some properties of relations. Specifically, we will consider 4 properties. The first is the property of being reflexive. Next, we will study the property of being symmetric. After that, we will discuss what it means to be anti-symmetric. And finally, we will finish with transitivity. And then we'll talk about some special types of relations that satisfy some of these properties. First, let's start with what it means to be reflexive. We say that a relation R on the set X is reflexive if x comma x is an element of R for all x in our set big X. We can consider some of the earlier examples we saw and see which of them were reflexive. So for example, the relation divides. This is reflexive on the positive integers because every positive integer divides itself. If you take a positive integer n divides n, because you can write n as 1 times n. Congruence mod 2 is also reflexive because integers are congruent to themselves any mod, not just mod 2, but any mod m. And that's because if you think about it, if you take any m, any positive integer m, it has to divide 0. 0 is divisible by any positive integer m, and 0 is equal to any integer minus itself. So we can say any integer is congruent to itself mod m. We also saw the relations associated with graphs. And in general, the edge relation for graphs it's not going to be reflexive in the graphs that we have considered. And the reason for that is because the graphs that we've seen so far in these videos, none of them have self loops. So sometimes people do study graphs with self loops. And it's possible if you have self loops on every vertex, then the relation associated with that graph would be reflexive. But we haven't seen any graphs like that yet. So the ones we've seen, their relations are not reflexive. Now let's go on to another property of relations, the property of being symmetric. We say that a relation on the set X is symmetric if for all elements little x and little y of our set big X, x comma y is in the relation if and only if y comma x is in the relation. If we have an undirected graph, the edge relation for that will be symmetric because for every ordered pair in the edge relation, u comma v, v comma u will also be in the edge relation. On the other hand, for a directed graph, it does not have to be symmetric. It can be, but it definitely does not have to be. The relation divides is not symmetric on the positive integers. For example, 1 divides 3, but 3 does not divide 1. And congruence mod 2 is symmetric. So if m is congruent to n mod 2, then we also know that n is congruent to m mod 2. Let's look at anti-symmetry. We say that a relation on X is anti-symmetric if for all elements little x and little y of big X, we have x comma y in the relation and y comma x in the relation only if x equals y. So the only way we can get both xy and yx in our relation is if x and y are the same. That's what it means to be anti-symmetric. For example, we can consider the relation divides on the positive integers. This one is anti-symmetric. If you have two positive integers, a and b, and you know that a divides b and b divides a, then you can deduce that a equals b. Congruence mod 2 is not anti-symmetric. So for example, if we look at congruence mod 2 on the integers, 2 is congruent to 4 mod 2, and 4 is congruent to 2 mod 2, but 2 does not equal 4. And if we take the edge relation for a graph, it will typically not be anti-symmetric. Now we'll consider one more property, the property of being transitive. We say that a relation on the set X is transitive if and only if for all elements little x, little y, and little z of our set big X, if we have both x comma y and y comma z in the relation, then we also get x comma z in the relation. Divides is a transitive relation. We can see that because if a divides b and b divides c, then a divides c. Congruency mod 2 is also transitive. If we have m is congruent to n mod 2, and n is congruent to s mod 2, then we get m is congruent to s mod 2. And if we have a graph, its edge relation will not necessarily be transitive. It can be, but it does not have to be. Now, we're going to finish up with discussing some special types of relations, which satisfy some of the properties that we just covered. We say that a relation on the set X is an equivalence relation if it satisfies the properties of being reflexive, symmetric, and transitive. For example, congruence mod m. This is an equivalence relation. We saw that it's reflexive. N is congruent to n mod m for any integer n. It's also symmetric. If A is congruent to B mod m, then B is congruent to A mod m. And we just saw that it was transitive on the last slide. So it is an equivalence relation. Divides is not an equivalence relation. So divides we saw was reflexive and it was transitive, but it was not symmetric because 1 divides 3, but 3 does not divide 1. Another special type of relation is a partial order. And we say that a relation is a partial order if the relation is reflexive, anti-symmetric, and transitive. So notice the difference between the equivalence relation and the partial order is the symmetry versus the anti-symmetry. The relation divides is a partial order. Divides we saw as reflexive because every positive integer divides itself. It's also going to be transitive because we saw if A divides B and B divides C, then A divides C. And the anti-symmetry we discussed as well. If A divides B and B divides A, then A equals B. One reason for that is if A divides B, then A is less than or equal to B. And if B divides A, then B is less than or equal to A. So if A divides B and B divides A, then A is less than or equal to B and B is less than or equal to A, which means that A equals B. Another example of a partial order is less than or equal to. So we can take some set, for example, the set 1, 2, 3. And less than or equal to, we can write this relation on that set as the set of these ordered pairs 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. And this set of pairs, the definition for this set is the set of x, y, for which both x and y are elements of 1, 2, 3, and x is less than or equal to y. And we got a total of 6 ordered pairs there. And this is a partial order. We can see with less than or equal to, it's reflexive because for any real number r is less than or equal to r. It's anti-symmetric because if we have real numbers r and s with r less than or equal to s and s less than or equal to r, then we need r equal to s. And it's transitive because if a is less than or equal to b and b is less than or equal to c, then we know that a is less than or equal to c. So that one is also a partial order. Another one that's a partial order that we've seen earlier in this course is subset. So we can do the same thing with subset that we just did with less than or equal to if we replace the set up here, 1, 2, 3, with a set of sets. we can define a partial order on that set of sets. And it will be a partial order because the subset relation is reflexive because every set S is a subset of itself. If we have a set R, which is a subset of S, and we have S also a subset of R, we know that all the elements of R have to be elements of S, and all the elements of S have to be elements of R. So that tells us that S equals R. That gives us the anti-symmetry. And the transitivity, if we have R subset of S, and we have S subset of T, we know all the elements of R are elements of S. And then we know all the elements of S are elements of T. That means that all the elements of R are elements of T. So we get R subset of T. And that's the transitivity. So that one, subset relation, we can see is a partial order, just like less than or equal to. And that's everything for partial orders. And thanks for watching.